Hello, and welcome to another edition of Focused on Physics. In this challenge video, we will learn how to analyze the motion of multiple objects. By the end of this video, you will know the physical parameter that links everything together. This video is the first in a new challenge series where we look at interesting problems with a focus on the underlying physics in each. Today's video, accelerating trains. Two trains face each other on adjacent tracks. They are initially at rest 40 meters apart. The train on the left accelerates rightward at 1.4 meters per second squared. The train on the right accelerates leftward at 2.2 meters per second squared. How far does the train on the left travel before the two trains pass? If you would like to try this problem on your own, pause the video here, then come back to see how you did. Before we get started, let's quickly review the kinematic equations. If you need a more in-depth tutorial on how to use these, please check out my kinematics video. Basically, we have 5 equations and 5 parameters. Each equation utilizes 4 of these parameters, and this chart provides a visual aid to see which parameter is not needed in each equation. Now, let's take a look at the problem statement once more. In most physics problems, drawing a picture is a must. If you are having difficulty figuring out how to get started, drawing a picture is usually a good way to go. With a picture drawn, we need to decide which way is positive and mark each train's position on the tracks. The usual convention is to choose right to be the positive direction, so let's stick with that. When analyzing motion, we need to concern ourselves with the starting and final states of our system. In this case, the final state occurs when the trains pass, denoted here in purple. Let's call this point D. Remember the tables from the introductory video on kinematics? We need to bring those back in, and each train gets its own table. This is because each train is governed by its own set of equations. We can plug in the values given to us in the problem statement. Don't forget that the train on the right is accelerating in the leftward, or negative, direction. Hence the negative 2.2 we listed in the table. Now, let's take a look at the displacement of the trains. Displacement is calculated by finding the difference between the final and starting locations. The left train started at 0 and ended at D, while the right train started at 40 meters and also ended at D. Using this, we can write down the displacement for each train and then place the results into our table. It may seem like we are stuck here as there is no more information given about each train. However, there is a key parameter that links the two together. Both trains start their motion at the same time. If we place stopwatches on each train, they would read the same time throughout the problem. That is, t left equals t right. In fact, time is almost always the linking parameter. Let's add this to our table. On the surface, time doesn't seem to help us out much here. After all, we don't know how long it took for the trains to pass each other. Even so, let's keep going. At this point, we have 4 of the 5 parameters filled out for each table, which means we have enough information to use a kinematic equation. Looking at our options, we want the equation that doesn't require the knowledge of the final velocity. Scrolling down the list, we land on the second equation. Let's write it down. Keep in mind that each train is governed by its own set of equations. This time around, each train will use the same principal equation, but that isn't always the case. Let's substitute in each train's displacement from the table. The left train's equation becomes d equals 1/2 its acceleration multiplied by time squared. The right train's equation is similar. d minus 40 equals 1/2 its acceleration multiplied by time squared. We now have 2 equations with 2 unknowns, something that is very solvable. One method is to solve the first equation for time, substitute that into the second equation, and then solve for d. That will work, but I want to show you a different way, using a ratio. Here, we write the left side of each equation as a ratio and set it equal to the right side as a ratio. This method works well because the train started from rest, leaving only one term behind. The beauty is now how we can easily cancel out the 1/2 and the time squared factors, leaving us with d and each train's acceleration. After a few steps of algebra, this problem will be solved. Let's start by multiplying d minus 40 to the other side, and then distributing AL over AR. We then subtract that first right-hand term to the other side, which allows us to factor out d. We can now divide by the difference to isolate d. With our variable of interest isolated, we can plug in the values for acceleration. The negative signs will cancel, and 1.4 divided by 2.2 is 0.63. Plugging this into our calculator gives a final answer of 15.6 meters. Let's double check the problem statement and make sure our answer seems reasonable. The right train's acceleration is greater than the left's, so we expect them to pass closer to the left train's starting point. Our answer is less than the midway point of 20 meters as anticipated. Finally, let's state the solution in English. The train on the left travels 15.6 meters. And with that, we've managed to solve another physics problem. After having gone through this example, you should now understand that multiple objects in motion require a different set of equations for each object. You should also understand that these objects are linked by a physical parameter, usually time. While time isn't guaranteed to be the time property in every situation, it is the best place to start when analyzing the motion of multiple objects. Thanks for watching Focused on Physics. If you enjoyed this video, subscribe, hit that notification bell, and give this video a thumbs up. Leave me a comment to request new content for an upcoming video. Until next time, stay focused.